moving on to the next section here. And okay, now we're moving on to the next section here. And we're on page 442 through 444. So we're going to start here on number 8 here on that page. And it looks like 5 to the power of 9 over 5 to the power of 2. Now, if you recall, this basically means you have 9 fives multiplied together. So that's 5 times 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 5 in the numerator. And in the denominator, we have 5 squared, which is just 5 times 5. Now, notice that since we have a fraction here, we can cancel, right? Multiplication, when these are multiplied together, you can cancel within a fraction like this. So we can cancel 2 of these 5s with the 2 that are down here. And what we're left with is 7 fives multiplied together. So this is the same as 5 to the power of 7. So you don't have to write this all out every time, but if you ever forget what to do, you could always just expand everything out. But what you should see is that these powers, when you're writing them as a fraction, these powers, as long as you have the same base, these powers subtract each other, right? 9 minus 2, that gives you 7. So let's look at an example problem number 9. We have 2 to the power of 7/3 over 2 squared. So again, we could subtract these powers. So our answer is going to be 2 to the power of something. And to find that something, what we're going to do is subtract these powers. So we're going to do, let's kind of do it to the side here. So we have 7/3 minus 2. Now, instead of thinking of it as just plain 2, we could think of this as 2 over 1. And when we subtract fractions, we want to make sure they have the same denominator. So we could change both these denominators to thirds. The first fraction doesn't change. It's already in thirds. And the second fraction we could change to thirds here. To change the second fraction to thirds, we multiplied the denominator by 3. So we have to multiply the numerator also by 3. So that gives us 7/3 minus 6/3 is 1/3. So always remember, whenever adding or subtracting fractions, you need a common denominator. So since the first fraction's in thirds, we could just change the second fraction into thirds, and then we'll have a common denominator. Okay, so essentially what we did here was subtract these powers. 7/3 minus 2 gives you 1/3. So our answer will be 2 to the power of 1/3. Okay. Later on, we're going to talk more about fractional exponents, but that'll be much later on. Just know that when you have powers, you're going to subtract those powers when you're dividing. Okay. Number 10, similarly, we have 3 to the power of 2, or in other words, 3 squared, over 3 to the power of 5. Again, we subtract these powers. That's going to give us 3 to the power of, well, what's 2 minus 5? Well, that's negative 3. 2 minus 5 is negative 3. If you recall, you could also write that as 1 over 3 to the third, right? Because when you have a negative exponent, you can make it a positive exponent by putting in the denominator. Okay, question 11. We have 5 squared times 5 to the third over 5 to the third times 5 squared. Well, we can combine these on top here, right? When we're multiplying, we add the powers as long as the base is the same. So here we have base 5, so we're going to go ahead and add those powers. So we can rewrite the numerator as 5 to the power of 5, adding these powers. In the denominator, we have 5 to the power of 5 again, right? You see that? Adding these powers because they have the same base and we're multiplying. So what do we do here? We can subtract those powers. So we can call this 5 to the power of 0, which is, of course, 1. Anything to the power of 0 is 1, just as a reminder. Okay, question 12. I'm going to go ahead and let you do that one on your own. Question 13 we could do together. This one features fractions. So let's work on that. But I'm pretty sure you could do it on your own. But I'll just do it with you just in case. So we have 9 to the power of 3/4 over 9 to the power of 1/4. So again, we want to subtract these powers. So this is going to give us 9 to the power of, and we want to subtract these powers. So we're going to do 3/4 minus 1/4. Now, do these denominators match? Well, yes, they do. These denominators already match, so we can just subtract them. So 3/4 minus 1/4 is 2/4. And of course, we can reduce that down 2/4 as 1/2, right? 2 is half of 4, right? So this would be 9 to the power of 1/2. Number 14. Here we have d to the power of 14 over d to the power of 17. Now again, we could subtract the powers. This would be d to the power of, and we do 14 minus 17. So that's d to the power of -3, right? Because 14 minus 17 is -3. And of course, we could rewrite that as 1 over d to the third. So keep in mind, whenever you see that negative power, you can put it in the denominator, and that makes it a positive power. Okay. 15. N to the power of -1 over n to the power of -4. So here we're going to have n to the power of, and what we're going to do is -1 minus -4. So again, we subtract the powers. So -1 minus -4. Now, I hope you remember that when we see this negative like that, that's going to make that a plus. So we can rewrite that as -1 plus 4, which is 3. So this is the same as n to the power of 3. Excuse me. Number 16. Here we have 5s to the power of -7 over 10s to the power of -9. Okay. First, let's talk a little bit about the 5 over 10. So let's just pretend we have a fraction 5/10. How could we reduce that fraction? Well, hopefully you can see that these 5 and 10, they have a common divisor of 5. So you can divide both top and bottom by 5 to reduce this fraction. That gives us 1/2, which makes sense because 5 is half of 10. So reducing the 5 over 10, that already gives us 1/2. Okay, so now we've basically worked with these coefficients here. But let's go ahead and figure out, it's going to be s to the power of what? So to figure that out, we again subtract the powers. So when we see that same base, we subtract the powers. So that's -7 minus -9. Again, this minus negative makes that a plus. So this is the same as -7 plus 9, which will be 2. So this will be s to the power of 2. And we're going to go and put it on top. So s squared on top. Here you don't necessarily need that 1 here. So you might see it also without that 1, because 1 times s squared is just s squared, right? 1 times anything is just that thing. So you're very going to commonly see like 1x, but just you may also just see that as x, right? Or 1y, you'll often see that as just y. Okay, so that's a very common thing you're going to see in algebra a lot. But just know that when you see x, that's the same as 1x, or these are the same thing. Okay, which makes sense, hopefully. 1 times x is just x. Okay, 17. Here we have x to the power of 11, y to the power of 3, over x to the power of 11, and just a y. So when you have just a y here, like with no power, you can consider that as to the power of 1. Okay? Anything to the power of 1 is just itself. So just a plain y, you could just write that as y to the power of 1. And hopefully that makes it a little bit easier to think about. Now, all the x's are going to cancel, right? These are all going to cancel. And then here we have y to the third over y to the power of 1, which is just y squared. Again, subtracting the powers. 3 minus 1 is 2. Number 19. Here we have 10 m to the sixth n to the third over 5 m squared n to the seventh. Okay. So again, the 10 over 5, we can make that 2 over 1. Or in other words, just 2 on top. Now, what about the m's? Well, you could see that we have more m's on top, right? So you could think of it as the m to the power 6, the sixth power minus the squared, right? 6 minus 2, that's 4. So we're going to have m to the power of 4. Now, what about the n's? Well, here we have n to the power of 3 on top, and then n to the power of 7 in the denominator. Well, again, we can subtract those powers. But one way to kind of think about it is if I were to expand it, you would have 3 on top and 7 on the bottom, right? 7 n's on the bottom, 3 n's on top. And they would cancel, but you would be left with 4 n's on the bottom. So another way to look at it is they cancel each other, and wherever there's more of them, that's where they remain, right? So just like for the n's, we would have 3 n's on bottom and 7 on, or 3 n's on top, I should say, and 7 of them on the bottom. Three of them canceling, leaving you with 4 n's on the bottom, and you can rewrite it like that. So you could always look at it like they cancel each other, and wherever there's more of them, that's where they stay. Okay, so again, they're subtracting each other, but just keep the n's wherever there's more of them. Same idea with the m's here, right? 6 minus 2 is 4. Obviously, there's more on top in this case, so the remaining ones stay on top. Okay, this will be a much faster way to think about it, and I'll show you more how to think about that in this next one. So here we have 3 squared, and we have m to the fifth, and t to the sixth over 3 to the fifth, m to the seventh, and t to the negative 5. Okay, so this one's a little bit different than what we've seen before. But you see how this has a negative power right here? You could always do the 6 minus negative 5 to figure that out. But another way to think about it is that, and this is kind of the way I like to think about it, is if you see a negative power, it's best just to switch where it's at right away. So if I see this negative 5 here, I can put it on the top. Any negative powers need to switch where they're at. So if it's negative on bottom, it can go on top, and then it'll change its power from a negative to a positive. So I could rewrite this as 3 squared, m to the fifth, t to the sixth, and then these t to the fifths will come up and become positive once they do. On the bottom, I just got this t to the negative 5 moves up, but they still have the 3 to the fifth and the m to the seventh. Okay, so now I can combine those t's, right? So I got 3 squared, m to the fifth, t, here they're multiplying, so we add those powers, t to the 11th, over 3 to the fifth, m to the seventh. Now, from where we're at, we could subtract those powers, right? So we have 3 squared on top, 3 to the fifth on bottom. Well, they would cancel each other, but you'd have 3 to the third on bottom, right? Because you have more on bottom. The m's, well, we have m to the fifth and m to the seventh. So what is that going to leave us with? Well, m squared. Would that m squared go on top or on bottom? Well, the m squared would go on bottom, right? Because you have more on the bottom. The t to the 11th has no one to cancel with, so we're just going to rewrite it just like that. Okay, I hope that made sense. I hope you're following along. And let's just go and move on to number 23 here. So this is 12, a to the negative 1. You can see they're just getting more and more complicated here, adding more variables. B to the 6th, c to the negative 3, over 4, a to the 5th, b to the negative 1, and c to the 5th. Okay. So again, we got some negative powers all over the place here. The 12 over 4, let's start with that. You could just make that 3. Because 12 divided by 4 is 3. Right? Or in other words, dividing both top and bottom by 4 gives us 3 over 1. Over 1 doesn't matter, right? Now, here, let's start moving around our negative powers, right? Because if it's a negative power, it really belongs on the other side, right? So we have a to the power of negative 1. That's going to come down here. There's also an a to the 5th down here as well. I'll go ahead and write that as well. So we have the a to the negative 1 that came down. This b to the negative 1 that's in the denominator, it needs to come up into the numerator. So on the top, we're going to have the b to the 6th that's already here. And then this b to the negative 1 will come up on top, becoming b to the positive 1. Same idea with the c's. Here we have a c to the negative 3 on top. It needs to come on the bottom, and it'll become a c to the positive 3. Remember, those negative powers, whenever you move them, they become positive powers. And generally, we prefer things written in positive powers. That's usually what you're going to see on tests and so forth. Okay, so equals. So on top now, we have 3b. Well, b to the what? Well, here we have 6 and then a 1. We add those powers. Remember, when we're multiplying, you add those powers. A to the power of 6. C to the power of 8. Adding the powers, adding the powers. Okay, moving along. Number 24. Here we have 5.2 times 10. So here we have some scientific notation. Times 10 to the power of 13 over 1.3 times 10 to the power of 7. And it says here, write your answer in scientific notation. So we want our answer in scientific notation. So one thing we can do first is divide these coefficients, these front parts. So 5.3 divided by 1.3. So let's go ahead and get our calculators. 5.3 divided by 1.3. Here I've got, and let's just go, you would call this 4 point. In this case, we're going to round to the nearest 10th spot. So that's the first decimal place. So that's going to be, you should see 4.07692, blah, blah, blah. But we're just going to round to the first decimal place. So that's going to be 4.1. So that 0 rounds up to a 1 because of the 7 behind it. So make sure you see that on your calculator. And then times 10 to the power of, and what do we do with these powers? We subtract them, right? So 13 minus 7, what's that going to be? Well, it's going to be 6. So it's already in scientific notation, so that's great. Number 25. Here we have 3.6 times 10 to the power of negative 10. And again, if you write everything that I write, it'll help you a lot, okay? Just always write what I write, and it'll make a lot more sense as we're going through. And if I say anything interesting that you think you want to remember, write that down too, okay? And obviously, anything I tell you to write down, you should write down. Okay, so we got 3.6 divided by 9. Let's go ahead and multiply those coefficients. So we got 0.4, okay? Make sure you're doing this on your own with your own calculator at home as well. Then we have negative 10 minus negative 6, because remember, we subtract these powers. So that's negative 10 minus negative 6. Okay, so that's the same as negative 10 plus 6. Well, that's negative 4. So In scientific notation, we actually want to write, we're okay with negative powers in scientific notation. We don't mind that at all in scientific notation. Okay, now is this correct scientific notation? Well, not quite, because we want the decimal to have one number in front of it, a number that's not a 0. So here we want to move the decimal one place to the right here, making it 4 times 10. And since we moved it to the right, we're going to go ahead and decrease the power by 1. Okay. So when you move it to the right, you lower that power of the 10. If you move it to the left, you increase that power of 10. Okay. And you could always make sure by putting both these things into the calculator, you should get the same answer. So that's always one way you could always check. 32. Ooh, we have a word problem. So go ahead and look at problem 32 on page 443 and just follow along. I'll read it aloud. It says the sun's mass is 1.998 times 10 to the 30 kilograms. Saturn's mass is 5.69 times 10 to the 26 kilograms. How many times greater is the mass of Saturn? How many times as great as the mass of Saturn is the mass of Sun? Wow, they really worded that as confusing as possible. But basically what we're going to do is we're going to divide the sun's mass divided by the Saturn's mass. And then what that'll give us is how many times greater is the sun's mass. So we're going to have 1.998 times 10 to the power of 30. And then the Saturn's mass, 5.69 times 10 to the power of 26. Okay, so we can start by dividing these coefficients. 1.998 divided by 5.69. So this gives us 0.351, we'll say, times 10 to the power of, and again, you subtract these powers, so that's going to be to the power of 4. This isn't quite in scientific notation. We're going to have to move it to the right once. So that's going to be 3.51 times 10 to the third. So remember, when you move the decimal to the right, you decrease the power. We decrease the power by 1. Okay, 33. Simplify each expression. Okay, so here we have 3/8. And then it says squared. So 3/8 squared. So when you see a fraction with an exponent, there's a couple ways you could think about it. But I would say the simplest way, and the way I want you to think about it, is that this squared goes to both the numerator as well as to the denominator. So you could rewrite this as 3 squared over 8 squared, right? This power goes to both the numerator and the denominator. Here, 3 squared, that means 3 times 3. So we can write that as 9 over 8 times 8 is 64. This fraction does not reduce, so that's as simplified as we can get. Number 34, we have 1 over a to the power of 3. By the way, to the power of 3, you'll often hear it worded as cubed. So you could hear this, what I just wrote here can be read as 1 over a cubed, okay? Or 1 over a to the power of 3, same thing. So I might use those terms interchangeably. Cubed and to the power of 3 mean the same thing. Okay. So here we have 1 over a cubed. So that would make 1 cubed over a cubed. Okay, well, what does 1 cubed mean? Well, that means 1 times 1 times 1. Well, that's just 1. Right? 1 times 1 times 1 is just 1. Here, a to the power of 3, and we'll just rewrite it like that. Okay? Okay. 35. Here we have 3x over y, and this is to the power of 4. So here, everything is going to get to the power of 4. So we're going to have 3 to the power of 4, x to the power of 4, and y over y to the power of 4. So this fourth power goes to everything in the parentheses. That's kind of the key. It goes to everything in the parentheses. If there was something outside the parentheses, then that fourth power would not go to that. But everything in the parentheses, where that fourth power is, gets that fourth power. So here we have 3 to the power of 4. You could use your calculator to figure out what that is, but it's 3 times 3 times 3 times 3, which is 81. X to the fourth over y to the fourth. Moving along, question 36. Same idea. We have 2x over 3y to the power of 5. See if you could do this one on your own. All right, I'm going to let you try this one on your own. Give it a try. Number 38. Here we have 2 squared over 2 to the third, or 2 cubed, to the power of 5. So this whole thing is to the power of 5. Now, I hope you remember, but when we have a power to a power, what you do is you multiply those powers. So here we have 2 to the power of 2, and then to the power of 5. So what we do with those powers, power to a power, we multiply those. So that's going to be 2 to the power of 10 over 2 to the power of, again, 2 cubed, and then to the power of 5, power to a power, you multiply those. So that's 2 to the power of 15. Now, I hope you remember, you can go ahead and cancel those powers, subtract them, but we're going to have more on bottom, aren't we? So that's going to be 2 to the power of 5 on bottom. All of them cancel with on top. If everything cancels on top, we still put a 1 up there. Yeah, we still put a 1 in the numerator. We could write 2 to the power of 5 as 32. Okay, remember 2 to the power of 5 means 2 times 2 times 2 times 2 times 2, which is 32. 54. Another word problem. During 1 year, about 163 million adults over 18 years old in the United States spent a total of about 39 billion hours online at home. On average, how many hours per day did each adult spend online at home? So they want us to write them both in scientific notation. So first, 163 million. So I'm going to go ahead and write that number. This is the number of adults. 163 million. Okay, so this is that number right here. This is how many adults. And then we have 93 billion hours. So that's 93. Okay, just like that. So we want to figure out how we can write these both in scientific notation. That's the first thing. So we could write this in scientific notation. Remember, when we have a number, the decimal is inherently at the end, right? Whenever we have a whole number, the decimal is at the end. So how do we move this into scientific notation? Well, we want to move that decimal until it's just between the 1 and the 6 here, right? So we're going to move it 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be 1.63 times 10 to the 8th. What about 93 billion? So let's go ahead and move the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is going to be 9.3 times 10 to the power of 10. Okay, so we wrote them both in scientific notation. Now we want to convert to hours per day. So hours per day, basically we're going to divide well, I guess it says on average, how many hours per day did each adult spend online at home? So So to find the average, what the average person spent, you would take the number of hours spent divided by the number of people. And that'll tell you how much each person spent. So it's going to be 9.3 times 10 to the 10th over 1.63 times 10 to the 8th. So what we can do here is divide the coefficients here. So 9.3 divided by 1.63, we're going to call that 5.7 times 10 to the, and here we would subtract these powers, so squared, just like that. You can leave the answer in scientific notation, or you can convert it to standard form, which would be 570. These are equal. Number 55A. Okay, we're almost done. 55A. During 1 year, people in the United States older than 18 years old watched a total of 342 billion hours of television. The population of the United States older than 18 years old was about 209 million people. Question A, on average, how many hours of television did each person older than 18 years old watch that year? Round to the nearest hour. So we're going to take the total number of people, which is 209 million. So 209, 0, 0, 0, 0, 0, 0. That's 209 million. And we're going to divide that. Actually, that's going to go in the denominator. The number of hours we're going to put in the numerator. So that's 342 billion hours. So that's 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so 342 billion hours divided by the population of 209 million people. So 342, 0, 0, 0, 0, 0, 0, 0, 0, 0, divided by 209, 0, 0, 0, 0, 0, 0. It says round to the nearest hour. So in our case, that's going to be 1,636 hours. So that's how much according to this problem, that's how much time the average person spent in that year watching television. That's a lot of time watching TV. 55B, on average, how many hours per week did each person watch per year? Okay, so if this is the total number of hours in the year that someone watched, we want to divide that into weeks. So how many weeks are in the year? I'll divide by 52. Okay, so there's 52 weeks in a year. You just need to know that for this problem, I guess. So we do the 1,636 divided by 52. So the average person in the United States spent about 31 hours watching television each week. That's like a part-time job watching television. Okay, 82A. Okay, so we're going to do A, B, and C of question 82. So that's on page 444. Finance. In the year 2000, the United States government owed about 5.63 trillion to its creditors. The population of the United States was 282.4 million people. How much did the government owe per person in 2000? So we're going to take the debt, which is 5.63 trillion. So that's 5.63 times 10. So trillion comes after billion. Okay, so what power we're going to do here? Well, it would be 3 for the ones, tens, hundreds, then 3 more for those thousands, then 3 more for those millions, and then 3 more for those billions. So I think that's to the power of 12 here. Okay. Right, because I think we did billions had like 7. something like that. Okay. And then we're going to divide by the number of people, which is 282.4 million, which is 282.4 times 10 to the 6. Let's go ahead and we can divide the coefficients here. 5.63 divided by 282.4, which gives us we'll say 0.02, rounding to the nearest hundredth. Hopefully you can see that there. And then times 10 to the 6th. Which is roughly about 20,000. So if you take the country's debt and split it amongst its population, each person would owe 20,000. Okay. 82B. In 2005, the debt had grown to 7.91 trillion. 7.91 trillion. With a population of 296.9 million. 296.9 million. So times 10 to the 6th. How much did the government owe per person in this case? So again, let's divide the coefficients. 7.91 divided by 296.9 gives us 0.0, and let's just go 3 decimal place here. So 0.027. And that's going to be times 10 to the power of, again, subtract these powers, to the power of 6. So what would that be in standard form? Well, that would be move the decimal 6 spots, right? So that's going to be 270,000. So 27,000. So in the year 2000, each person owed 20,000. Now in the year 2005, each person owes 27,000. What was question C? What was the percent increase in the average amount owed per person from 2000 to 2005? So hopefully you remember how to do percent increase. You take the bigger minus the smaller and divide by the original. So we're going to take 27,000 minus 20,000 and divide by the original, which 20,000 is the earlier number here. So that's going to be 7,000 over 20,000. We can cross off 3 zeros here. So 7 divided by 20, which equals 0.35. So 0.35, that's 35%. So it was a 35% increase in debt per capita. Okay. Page 490. Let's go ahead and do this last section here. I think this is the last section, right? Yeah, last section. Woohoo. Okay. Page 490. Starting with question 16 here. And basically here, we're covering combining like terms. So we have, in this case, 12p squared plus 8p squared. Now, when it comes to adding or subtracting, this is very different than what we just covered with multiplying and dividing, okay? Here, you can only combine things if they have the exact same variable. So here they both have p, so that's the same variable, and they have to have the same exponent. So p squared, p squared. So since they both have p squared, we can go ahead and add these. And what you do is you just add the coefficients. So 12 plus 8 is 20. So the answer is going to be 20p squared. Okay. You do not add these powers. Okay. Don't put p to the fourth. You do not add these powers. Okay. Only if we're multiplying. If we were multiplying these two together, then you would add the powers. But when you're adding or subtracting, don't do that. It just stays p squared. Okay. Very similar to adding or subtracting fractions. You don't add the denominators. Okay. Question 17. We have 2m cubed n cubed plus 9m cubed n cubed. Again, they have the same variables and the same power, so we can just add the coefficients. So that's 11 m cubed n cubed. 18. 8w squared x plus w squared x. I hope you remember me talking about this one. We could think of it as just 1w squared x, right? So we have 8w squared x plus another 1w squared x. So that's going to make a total of 9w squared x. Why don't you try number 19 on your own? Let's do number 20 together. So here we have x to the third minus 9x to the third. Okay, again, you can consider this a 1 in front of this. So what would be 1 minus 9? Well, that's negative 8. X cubed. Okay, try number 21 on your own. Try number 22 on your own. And here we'll do 23 together. So this would be 5b c to the fourth minus 13b c to the fourth. So what's 5 minus 13? Well, that's negative 8 b c to the fourth. And that's it. Okay, well, I hope that made sense. Hope you're able to get through it. And after this is the review. I've already made a video about that, so you can go ahead and check that out when you have the chance. Go through the review, and if you did well throughout this and you do well in the review, you should do well in the test. All right. And if you have any questions, you could always email me, and you can make an appointment to see me as well. My email is ttrigg@ofy.org. Okay, well, thank you, and I'll see you next time.